In this video, we are going to talk about planes. The general equation of a plane is going to be something like ax plus by plus cz equals d. But it'd be very helpful to find out where these numbers come from. Again, very similar to what we did with lines, we are going to have to use vectors to do this. But unlike lines, we cannot tell the direction of a plane from just one vector that is parallel to it. We could do that with two vectors. So, say, have two vectors here, and we can imagine the plane that contains those two vectors. That would be good enough, as long as these aren't parallel vectors. If they are parallel, that wouldn't be quite as useful. But having two vectors is a little bit more complicated than we'd like it to be. In fact, if we had two vectors, we'd end up with 6 different components, and that'd be far more than the 4 numbers that we're going to need to actually give the equation of the plane. So what we're going to do, instead of using two vectors that are in the plane, is we're going to use a vector that's perpendicular to the plane. So here, so imagine we have our flat plane, but then a vector sticking up out of it. Such a vector is frequently called a normal vector. Normal here is kind of like orthogonal. It's kind of a formal term for talking about things that are perpendicular. I know there's a lot of different terms that seem kind of weird why we need three different terms for perpendicular, but that's the way mathematics has evolved. So that's the term that's used for this vector. And usually we'll use a lowercase n, sometimes a capital N. Obviously you can pick whatever letter you want technically, but I'm going to stick with a lowercase n. We're also going to need a point on the plane. Obviously, you can talk about various parallel planes. So imagine another plane down here that's parallel to it. Well, an equivalent vector in would be normal to that plane as well. So we will have to have some point that is on our plane. So we could say a p naught, which is x naught, y naught, z naught. So very similar to what we did in developing our lines. Now, what does that really mean for us? Well, let's actually redraw this a little bit. Maybe I should have put the point P naught at the base of the vector in. So now we want to pick some other point in our plane. Let's say a point P over here. That is x, y, z. And we want to imagine how we would associate this point P with the vector in. Well, keep in mind, if we were to draw the line segment between P naught and P, that's going to have to be perpendicular to n. Or in other words, if we can somehow get a vector here, that vector would have to be perpendicular or orthogonal to the vector n. We can actually go ahead and do that. Remember, we can form what we call position vectors. Let's say the position vector of the point P naught, we'll call that R naught, which is going to just be the vector from 0, 0, 0 to x naught, y naught, z naught, which just has the components of x naught, y naught, z naught, and then the position vector from going from the origin to P, so from 0, 0, 0 to x, y, z, which is just going to be x, y, z. This vector here is just going to be formed by subtracting these two vectors. So in fact, the vector here from P naught to P is just going to be R minus R naught. You can even think about it in terms of how you find the vector between 2 points. We take the terminal point coordinates minus the initial point coordinates. So this is just the vector x minus x naught, y minus y naught, and z minus z naught. this vector is going to have to be perpendicular to n, to the normal vector n. Well, how do we tell whether or not two vectors are perpendicular, or to use the more formal term, orthogonal? Well, that's just in the dot product. The dot product of two orthogonal vectors is 0. In fact, and it goes both ways. If the dot product is 0, then they have to be orthogonal. So that's what we have here. We just take the dot product of the normal vector n with this difference. So here we have the vector equation of our plane. Oops. But similar to lines, that can be a little bit complicated to really unpack if you're not really thinking as much in terms of vectors. It would be nice to actually get this without vectors, so that's what we're going to do. We're going to go ahead and give components to our normal vector n. Just going to say it's ABC. And then remember, if we start with n dot product with r minus r naught, and we want that to equal 0, this is ABC dotted with, and in fact I already wrote this out, is x minus x naught, y minus y naught, z minus z naught. And we want that dot product to equal 0. And remember, we find the dot product by taking the components of this vector times their corresponding components of this vector, and then adding all those up. So we have a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And we want that to equal 0. And you can say this is the scalar equation of the plane through that point with that particular normal vector. So you can already kind of see exactly where the equation that I had before comes into play. The coefficient of x here is just going to be a, coefficient of y here is going to be b, and the coefficient of z here is going to be c. All the other terms are just going to be constant terms. In fact, what I like to do is I like to just go ahead and pull out the terms that are not constant and move all the other terms to the other side. We're going to have the ax plus by plus cz is going to equal some constant. I'm just going to call that d. Or, well, the book actually does this a little bit differently. It leaves the d over here. Technically, their d and my d are different. They're multiplied one by a minus sign, and we get the other one. But the point here is that the main core feature of this is that we have these non-constant terms of ax plus by plus cz, where the a, b, and c come from a normal vector. The d here we get by just using our point that we plug into our plane, or that is on our plane, and we can basically just get it by plugging the point into the ax plus by plus cz on this side. So normally I'm going to go ahead and just leave finding d out till after I've actually used my normal vector to get this left-hand side. And note what that means is that if we have any two parallel planes, well, they're going to have the same normal vector, so they're going to have exactly the same left-hand side. Though we can actually multiply or divide by a number if we want to. Technically here, any vector that is parallel to n actually works. But they're going to have different d's. That's the main thing that's going to be different here, is the d. But we can also go the other way. If we have the equation of our plane, we can find a normal vector by reading off the coefficients of x, y, and z. That'll give us a nice normal vector, and that'll give us an idea, based off the equation of the plane, what direction the plane is going. And we can actually use that in various ways. Though I'm not sure if we'll go through any examples in this video, There are examples in the book, such as being able to find the distance between a point and the plane. So let's do a couple of examples, or a few examples. I'm going to actually work out quite a few of these. So here, our directions are just find an equation of the plane. Unlike with lines, we don't really need to have multiple different types of equations. Normally, we don't really want to write the vector equation. We just want to go ahead and write that normal scalar equation that we saw on the previous page. So here we have a point. The point here is a little bit hard to see maybe, but it's just going to be the origin. And it's going to be perpendicular to this vector. Or in other words, this vector is normal to the plane. So this is our ABC. And so really all we need to do is use that in our equation. We have A is 1, so we have 1 times x, then plus b times y, but b is negative 2, so we have a negative 2y, and then plus c times z, so that's plus 5 times z. The number that we get over here, we can just say, well, plug in the point. If we plug in the origin of 0, 0, 0, and basically just plug in 0, 0, and 0, and what you're going to get out is 0. And that's all we have to do. When we have a normal vector, and we can go ahead and plug in the point, and out pops our equation. In this problem, we have a very similar thing. We have a point on the plane, though it's not the origin this time, and we have something that's perpendicular to the plane. This time it's a line instead of a vector. So we have to somehow get an idea of the direction, the normal direction, using this line. But what that means is that we want a vector that is parallel to that line. Because if it's parallel to the line, then it's perpendicular to the plane. Well, what do we do here? Well, remember how we actually worked with lines. For one thing, this is in parametric equations. So in parametric equations, the coefficients of your t are the actual components of the vector that's parallel to the line. So our normal vector in this case is just going to be 3, negative 1, and then 4. That vector is parallel to the line, and therefore is a normal vector to the plane. So now we have a point, we have a normal vector. We can do exactly the same thing as we did in 23, where we take these to be the coefficients of x, y, and z. So we have 3x minus 1 times y, then plus 4 times z. We're not going to have a 0 over here. Well, it's possible that we have 0 there, but only if it turns out that the origin is on the plane and we just didn't know to begin with. But we shouldn't expect it to be a 0. What we need to do is plug in 2, 0, 1 into x, y, and z and see what we get. So here, 3 times 2, 6, minus 0, so it's still 6, and then plus 4 times 1, so 6 plus 4 is going to give us a 10. This is the equation of the plane that passes through that point and is perpendicular to that line. These are actually going a little bit quicker than I was thinking they would. But here we have another problem, problem 28. We have a plane through a point parallel to another plane. So here it's kind of a little bit different than what we had before, where we didn't have something that's perpendicular, but we have a plane that is parallel to. Let's rearrange the equation of this plane. So we have z equals x plus y. Let's move the z over to the other side. So we have x plus y minus z equals 0. That's the equation of a plane. And you can kind of actually see that there's a normal vector to that plane. The normal vector being the coefficients of x, y, and z. So you can say it's 1, 1, negative 1. And we can use that normal vector because the plane that we're looking for is parallel to this. It should have the same normal vector. So in fact, we are going to essentially take these same things as the coefficients again of x, y, and z. Or in other words, all we're really doing is starting with x plus y minus z and having a different number over here. Or possibly a different number. Maybe it's the same plane, though we probably won't have the same plane. And we get the new number over here by seeing what happens with this point when we plug it into this equation, into this expression over here. So we have 3 plus negative 2, so we have a 1 so far, but then minus 8. So 1 minus 8 will give us a negative 7. And so that is the equation of that plane, of the plane that we're looking for at least. So note here exactly what I said before. We have a parallel plane, and that just really means that we have a different d, a different number over here. So pretty easy to find parallel planes. Next problem, we have a very similar thing to 28. We want the plane that is parallel to a particular plane but containing a particular line. Now, here actually we have a little bit more information than we normally need, because that line has to be parallel to the plane that we're talking about in the first place, or else there wouldn't be any possible solution to this. But we'll just take their word for it that this is a possible situation and look at what we do with it. So first of all, we note that we are talking about being parallel to the plane 5x plus 2y plus z equals 1. So our equation for the plane that we're looking for is just going to start with 5x plus 2y plus z equaling something. We don't know what that something is, but that's what we're going to have to figure out. Now, how would we normally find out what that something is? We would take a point that we know is on the plane and plug it in for x, y, and z. But we don't have a point on the plane right now. It's kind of unique compared to the other ones so far. But what's kind of important here is that it has to contain a particular line. It contains the line with parametric equations: x equals 1 plus t, y equals 2 minus t, and z equals 4 minus 3t. Can we get a point on that line? Well, we just plug in an easy t. Why not t equals 0? That's actually probably the easiest thing possible. If we do that, well, we just end up getting our constants. So we have 1, 2, and 4. That is a point that's on that line, and therefore is a point that has to be on that plane. And so if we plug in 1, 2, 4, we should actually get what we need. So we have 5 times 1 is 5, plus 2 times 2. So 5 plus 4 gives us a 9. Then we have to add 4 to that. 9 plus 4 is going to give us a 13. And this is a case where we could actually probably test whether this actually is true. We could pick another point on the line. So maybe we'd say pick t equals 1 this time. Then we'd actually get the point 1 plus 1, which is 2. 2 minus 1, which is 1. And then 4 minus 3, which is another 1. And if we go ahead and plug 2, 1, 1 in here, we should get 13 as well. So 2 times 5 is 10, plus 2 times 1, so 10 plus 2 is 12, and then plus another 1 gives us the 13 that we're looking for. So, in fact, you can kind of already see that this plane that we're talking about does contain 2 different points on that line that we get from our equations, and it's going to have to contain the entire line because of that. So it does contain that entire line, and it's definitely parallel to the plane that they gave us. So this is our answer. Now let's move on to problem 32. This actually looks like the most likely situation that we might be in, where we have 3 different points that are on the plane. But it turns out this seemingly simple situation is a little bit more complicated to work out, because we don't have a very quick and easy way of getting a normal vector. We only have points that are in the plane to work with. So let's start off by working with that information and getting some vectors in the first place. We're just going to find two vectors in the plane itself. And we can actually start with any point and end at a different point, as long as we don't use the same 2 points for both the vectors that we're going to work with. And since we have the origin here, let's just look at the vectors from the origin to the 2 points that we're working with. So I'm going to call one of them u. It's going to be the vector from 3, -2, or sorry, from the origin. So the initial point is the origin, and ending at 3, -2, 1, which that's just going to give us the vector 3, -2, 1. Same thing with going from the origin to 1, 1, 1. We're going to get another vector, which I'll call v, which is 1, 1, 1. These are two vectors that are in the plane. These are parallel to the plane. We need a vector that is not parallel, but perpendicular. So we need a vector that is perpendicular to both of these two vectors. How do we get a vector that's perpendicular to two vectors? Well, we use the cross product. You kind of can't avoid using the cross product here. So we'll say our normal vector is going to be the cross product of u and v, and we're going to have to figure out how to find that. Well, to do that, I'm going to go ahead and convert these into ij's and k's. So we have a 3i minus 2j plus k crossed with v is I plus j plus k. Then to take the cross product, I'm going to expand this out. Essentially FOIL it, but notice we do have 3 terms crossed with 3 terms. We're going to have a lot of terms here. Now, I'm also going to kind of skip writing down some of the terms because I know that 3i crossed with I is just going to be 0. A vector crossed with itself is 0, and the 3 doesn't really matter there. It's I cross I. So any time that I'm going to have a vector with itself, I'm going to leave it out. But all the other ones are going to need to be there. So I'm going to start with the 3i. I'm going to cross it with each one of these. Again, the crossing with I goes away, but I do have a 3 times I cross j. I'm going to have a 3 times I crossed with k. Now I move on to negative 2j crossed with all 3 of these. Again, the j is going to go away this time. So I have a minus 2 j crossed with I. And remember, I don't want to swap the order of the I and j here. The order is actually important. We'll have a minus 2 j cross k. I move on to k. So I'm going to have ki, kj, and then kk goes away. So plus k cross with I plus k crossed with j. And I'm going to have to simplify this. And just as a reminder, I like to use the cycle of I, j, k. I cross with j, I'm following the arrows when I do that, so I end up with a positive k. So this is a 3k. I cross with k, I'm now going against the arrows, and I end up getting a negative j. So this is negative 3j. J cross with I, again we're going against the arrow, so negative k. I already have a negative there, so I get a plus 2k. J cross with k, going with the arrow, so I get a positive I, but there's a negative there, so minus 2i. K cross with I, I'm following the arrows, and I end up with j. And then finally k cross with j, I'm going against the arrows, so I end up with a negative I. Or in other words, because we have to combine like terms essentially, we have a minus 2i, we have a minus I, so we have a minus 3i. We have a minus 3j, we have a j, so you end up with a minus 2j. Then we have a 3k and a 2k, so we get a 5k. Or if we prefer, you can actually rewrite this as minus 3, minus 2, 5. So a lot more work than we had to do on the previous problems, just because the cross product is kind of annoying, to be honest. But it is pretty straightforward. There's no guesswork involved here. It's just follow the pattern. If you do prefer using the determinant method for this, go right ahead. It gives you the same result as long as you do it correctly. But I'm going to continue doing them in this way just for those students that are not as familiar with determinants. Okay, so we have a normal vector. We have a vector that we know is orthogonal or perpendicular to the plane. And so now all we need to do is start with that. Those are going to be the coefficients of x, y, and z. And we're going to have to figure out what goes over here. What is our d in this case? And we just get that by plugging in our numbers. So plugging in one of our points. So I'm going to pick the origin. Origin's 0, 0, 0, and 0 is always nice to work with, as long as we're not dividing. If I plug in 0, 0, 0 here, well, everything becomes 0, so we should get a 0 over here. One thing that we can do to test ourselves is that 0 should be true no matter what point we pick on the plane. If we pick the points 3, minus 2, 1, and 1, 1, 1, and plug those in over here, we should still get 0. So let's actually test that. So negative 3 times 3 has a negative 9. Maybe I'll even write this out. So I'll have a negative 9. We have minus 2 times negative 2. It's going to become a positive 4. Then we have a plus 5 times 1. So we end up with a plus 5. And that, in fact, does equal 0. What about 1, 1, 1? Now, that one's a little easier to plug in, actually. So we just end up adding up our coefficients. We have a negative 3, negative 2, plus 5, and again we get 0. So you can actually see that this equation here does contain each of those 3 points, and so it's the plane that through those 3 points. So it'll be a little harder to find those coefficients directly from the 3 points, but when we use vectors and the cross product, it's not too bad. Alright, one more plane. Problem 33, and this is basically the same as the last problem, except this time we're not using the origin, so there'll be a little bit more work involved. But the process is exactly the same. So remember, the first thing we need to do is find vectors that are in the plane, because all we have are 3 points on the plane. And so I'm going to go ahead and just subtract one of these points from another point. And it really doesn't matter which two that we choose. So I'm going to take the vector u to be the vector from our second point here. Let's use the second point as our terminal point, and we'll use the 2, 1, 2 as our initial point. So I'm going to take 3 minus 2, give us a 1. Negative 8 minus 1 will give us a negative 9. And 6 minus 2 will give us a 4. For v, I'm just kind of looking for points where I don't have too many negatives, just kind of make it easier on myself. Let's actually take the vector from our third point to our first point. So we'll have, remember, we take the terminal point minus initial point for our components. So we take 2 minus a negative 2, so we'll get a positive 4. We have a 1 minus a negative 3, so we get another positive 4. Then we have a 2 minus 1 to get a positive 1. So we kind of got a weird situation where we have one vector going like this, but then we have another vector coming in like that, if we were to draw these out with our points. But it doesn't really matter. Any vector that's going to be perpendicular to both of these two vectors will be perpendicular to whatever order we put these in. So I'm just trying to pick combinations that give you positive numbers. Alright, so Using the cross product, take u cross with v, and that's going to be the n that we want. Again, I'm just going to write those out. So I minus 9j plus 4k. Then we cross that with 4i plus 4j plus k. We expand everything out. Again, I crossed with the 4i goes away. So we'll have 4i crossed with j. I don't know why I have the parentheses here. We have I crossed with k. Now we move on to the minus 9j. But then we have 9 times 4. So actually, do have to actually multiply numbers now. We have minus 36j crossed with I. We have a well, 2 j's together becomes a 0, so we don't need that one. But we do have a minus 9j crossed with k. Now we move on to 4k. We end up with a plus 16k crossed with I. And then another 16k crossed with j. The 2k's go away. And I'm going to continue actually drawing this out just to help. So we work out what all these are. I cross the j, we get a positive k. So 4k. I cross with k is a negative j. J cross with I is a negative k. We already have a negative there, so we have a plus 36k. J cross with k is a positive I. We already have a negative, so we have negative 9i. K cross with I is a positive j, so we have 16j. And then k cross with j is a negative I, so a minus 16i. Of course, then we also have to combine like terms. We have a minus 9i minus 16i. It's going to be minus 25i. We have a minus j, but a positive 16j, so we end up with a plus 15j. And then finally, 4k plus this 36k is going to be a 40k. Or in other words, this is minus 25, 15, and 40. Now, we could actually just go ahead and use this particular vector, but do note that any multiple of this vector is also a normal vector. If I multiply this vector by something or divide by something, I will get another vector that's perpendicular to the plane. So I'm going to go ahead and simplify this by just recognizing that everything here is a multiple of 5. So if I pull out a 5, I'll get a new vector. Let's just call it n2, which is negative 5, 3, 8. It's a nice simpler vector, so it'll save me some work when I actually have to plug in our points and find out what the d is going to be. So our equation, well, we just use the components here as our coefficients of x, y, and z. We have a minus 5x plus a 3y plus an 8z. And all I need to do is pick a point and plug it in to find out what my d is going to be. So I'm just going to go ahead and pick the 2, 1, 2. All of these should give us the same number if we plug it in. And this is a good check if you want to check whether or not I did all this right. You can pick the other points and see what you get. All of them should give you the same number. But if I plug 2, 1, 2 in there, so we have minus 5 times 2, so we have a negative 10. We have a plus 3 times 1, so negative 10 plus 3 is going to give you a negative 7. Then plus 8 times 2, so plus a 16. So essentially 16 minus 7 gives you a 9. And that's our answer. So like I said, try out the other points, see if you get 9 in those cases as well. If you don't get 9 in all those cases, then I did something wrong. it should work itself out. At least the process is correct. This is the process that you need to do in order to find this plane. All right, so I'm gonna leave that off here. There are homework problems where you have to find these planes that very similar ways, and that's all I really have to say for now. So I'll see you guys next week.